Hey guys, Vade here. Happy Pi Day 2024. And for Pi Day, I'm going to be talking about E because I think that E deserves at least the same amount of respect as pi. And hopefully, as you see through the things that I talk about in this sort of lesson here, why I think that. So, welcome to this lesson on Euler's number, often symbolized as E. Today we'll dive into its fascinating history, its applications, and why it deserves just as much, if not more, recognition as its more famous cousin pi. By the end of this lesson, I hope you guys will have a deeper appreciation for E and its significant impact on math, science, and even demography, which we'll talk about. So let's dive in. I just did the introduction. I probably should have went to this slide, but here this is E and this is pi. So let's first clarify a common misconception. Euler's number, which is what this lesson is about, E, approximately equal to 2.718, is distinct from Euler's constant, denoted as gamma, which is approximately 0.577. While E arises in exponential growth in calculus, gamma, right, Euler's constant, is related to harmonic series. So you'll see that in calculus as well in number theory. And both are named after the great mathematician Euler. But they serve entirely different purposes. So that's why for this lesson we're going to focus solely on E, the number, and its extraordinary versatility. But Euler's constant is also very important. It's actually not just Euler's constant. He shares it with another person. I don't remember his name, but he does share it with another person. It's not just his. By the way, just a picture here. I just screenshot from Desmos. These are essentially arguments. For these should be limits as n approaches infinity. Right here, and then of these, like for example, this summation and then this summation here. This is for Euler's constant, and this is for Euler's number. So since Desmos doesn't let me do infinite limits, I just picked a very large value for n, and as you see here, I got 0.578, right, which is pretty close to the 0.577, and here I got 2.716, which is pretty close to 2.718. Okay? So this is just sort of showing you where these come from. We're going to talk, since we're going to talk about Euler's number in this video, we're going to talk more about the 1 plus 1 over n to the n a bit later in this lesson. So, as I said, E is definitely below pi in terms of popularity, but after pi, E is arguably the second most famous mathematical constant, which is good because you first learn about E probably in algebra 2, at least in the U.S., and then or like pre-calculus, like that's when you first learn about it. So it's taught to a lot of Americans. Okay, maybe this is true in other places, but at least in the 10th grade, uh, people usually learn about E for the first time, which is great. Um, so it is arguably the second most famous mathematical constant, yet it often flies under the radar. While pi is celebrated for its elegance in geometry, right? We have like pi r squared, pi times diameter, 2 pi r, all that stuff. E is more deeply embedded in real world applications, right? E is a part of exponential growth, decay, compound interest, probability, and even demography, which we'll talk about in this lesson. Some argue, I'm kind of on that side, that E's applicability across disciplines makes it even more important than pi. So let's dive right into that. And by the way, the image on the screen here is just some funny meme I found online. Top 10, this is 10, right? Because log rules move the 10 out, ln of e is 1. So top 10 reasons e is better than pi. E is easier to spell than pi. E is used in calculus, while pi is used in baby geometry. I love this. Oh my god. Um, yeah. So let's talk about, demography. Okay, so one of the earliest applications of E beyond mathematics was in demography. Study conducted over 100 years ago by Wilhelm Lexus, whose picture's on the left here, used E to analyze population growth and survival rates. He applied the principles of exponential decay to model human mortality rates. And it really laid the foundation for modern population studies that we see today. And the reason why I'm showing this is because it really shows how E transcends this abstract math and directly influences societal understanding. Let me talk a little bit about this. So this is from one of Lexus's papers here, and it's a table, right? So it's sort of this experimental versus theoretical, okay? And people, after he died, applied his ideas to the distribution of male deaths in France, using the same age groups, or very similar age groups to what Lexus used. And so what they did here, which is actually really clever, is they used the Gaussian error function to get these theoretical outputs for the inputs, which are the ages, right? You plug in the age for you and you get some output. They used an error function to do this, which is kind of cool, right? And this error function, right? The error function has e involved in it, e to the negative t squared. So that's pretty cool. And if we actually look at this, right, the according to the theory is the error function, right? And then, of course, which is the non-bolded graph, and then the the bolded is the actual deaths according to the table. And really, what you see here is that at the beginning, younger ages, they're really far off, right? Like, number of deaths is significantly lower for lower ages based off of this theoretical function here. But as we get to the older ages here, it becomes pretty spot on, right? Especially we look at 85 to 90 and beyond, it's pretty much exactly the same. And so we're seeing here how the error function, which involves E, is related to a pattern, a distribution of male deaths in France. And how this is like real world stuff. So, and we're going to talk about this next, but this just shows how E is quote unquote natural, right? Because it kind of just flows with the world. E just connects naturally with the world. And so that goes on to my next point here. Or actually, no, this is not my next point. Sorry. Let's talk about this more, another application. Sorry, we're gonna get to that in just a second, or just a bit here. So this is continuous growth, the formula for continuous growth. I want to mention this, but this is of course taught usually in algebra 2 level. So a lot of people are aware of this formula. Of course, they probably maybe don't understand it as well as they don't understand it as well as they think, right? Because it's like, oh, P E R to the RT. Just know that P is principal value, R is rate, and T is time. That's it. Like, you just plug and play. That's great. You know how to do a problem using continuous interest. But what is it really? Well, principal, right? It's like, think of this. You're investing an amount. Like in this picture here, I invested $1,000. Okay, we have a rate of 0.05. Okay, this is our interest rate. And then T is years. So, and again, this is like a slider here. We like T is going to be increasing, and that's what this is. Like the T is the real input here, and we're inputting, and we're seeing that increase, right? Based off of our interest rate and how that impacts our total amount A as time goes by. So as we see here, if we go like with $1,000 with that interest rate of 0.05 after like let's say 10 years, we're like pretty darn close to the $2,000 mark. Now, of course, this interest rate is pretty bad, but it still shows, right? Like how my money, and again, we have to see here, of course, is it adjusting for inflation, all that kind of stuff. We don't even know what time period this is in, if I'm being completely honest. So we can't really, like, if this was like, adjusting for inflation, I'd be like, wow, yeah. But this just shows how we can use E to model how an initial amount invested with a given interest rate, uh, initial amount or principal amount, right, or amount invested, how that is impacted as time goes on with an interest rate. So that's really cool, and this is used in finance a lot as well. So very much used in the real world. We're going to talk more about that soon. So now going back to what we talked about earlier, with the 1 plus 1 over n to the n and how n equals to 1,000, we saw a pretty good approximation of E. So I'm just talking a little bit more about that. So this right here, I graphed in terms of x, 1 plus 1 over x to the x. I went really far in, so that's why it's not a straight line. Okay, if you go closer to like the origin, it's an actual like curve. But I wanted to, because I can't do infinite limits on Desmos. Okay, it's just not possible for me. I don't think it's possible for anyone. So I just, because infinite limits, it's all about, limits to infinity. It's all about M behavior. So I just went all the way like far right. And this is, of course, this is justifies that horizontal line here because it sort of approximately like converges to the E value that we know and love, which is the 2.718. So for example, you see here I went as far as like 5041.7, and I got to that 2.718 here. Of course, the rest is probably off, but this just shows, like, this is where we actually get E. This is one of the limits. There are other limits. There are other ways to get E, but this is one way we can see E get derived, where we can see E actually, coming from without just saying E, or without saying 2.718. This is where we see it come from. Okay, now, sorry, I told you guys earlier, I thought I was going to do it at the next slide, but there's some other stuff, important stuff still, keep in mind. But what makes E natural? And I talked about this, it flows with the world. It goes along with the world, right? As we saw with the demography, it was really interesting, right? Like something that involves the error function, Gaussian error function, how that as age increased, we saw it get really close, if not exactly the same as the actual experimental graph. Really interesting, but really, um, sorry, really what makes it natural, the natural, we think of it as like the natural base, because like e to the x, it's the base of the exponential function, or natural log, right? It's just logarithm with the base e, specific instance of the logarithm. It's because really e also just naturally simplifies calculations and calculus. Okay, and this is why, like, people, like, if you want a more explicit reason for why E is so important, you have to be studying calculus. That's just how it is. If we take the derivative of e to the x, d dx of e to the x, we get e to the x, which is extremely rare, right? Like, before you learned e to the x, you probably thought the only derivative that equals itself is the derivative of 0, because the d dx of 0 is 0. So now d dx of e dx and c dx, it's spitting out the exact same thing. This is true with the integral as well. Integral of e dx, indefinite integral of e dx equals e dx plus c. And we can use algebraic techniques and manipulation, exponent properties, log properties, whatever, with e to simplify some calculations. And of course, e dx, right, compared to like 2 to the x, right, derivative of 2 to the x is not 2 to the x. Derivative of 2 to the x with respect to x is just 2 to the x natural log of 2. That's different. But derivative with respect to x of e to the x is e to the x. So e is really the foundation of exponential and logarithmic calculations. So that's like an explicit way to think about it. It's natural. It just flows with our calculations. But of course, in the more abstract sense, thinking about real world sort of things here, it just naturally flows with patterns in our world, as we saw with demography, as we saw with continuous interest. And I'm going to mention some more here, right? Like E, right, is a universal constant, like in physics, right? Let me think of stuff in the top of my head here, like radioactive decay, right? Growth of electric charge, biology, right? You can model, right, population growth, as we saw, with demography, some more stuff in demography. Decay of ecosystems, right? Finance, continuous interest, which we talked about. Comp sci, right? This E is used in training large language models, right? Of course, that's just simplifying it, but E is definitely a part of some training some large language models, right? And that leads to AI, and AI is so important today, right? AI is, it's the AI era right now. So let me get the next slide here. So now let's talk about Euler's legacy. We're going to talk about the man who did it all. Okay, the man who got us this number, right? So Euler, he was a true polymath. He did a lot of stuff. This E was not his only thing. He did a bunch of stuff, such as the Euler's identity here, which comes from Euler's formula, and I'm gonna talk about it in just a sec. But Euler did a lot of stuff. Okay, he invented so many fundamental properties, and there's stuff that he's even done that he actually didn't get his name. He didn't get credit for, right? Just because, and the reason why he didn't get credit for some of the stuff he's done, which is pretty fundamental in math still, is because he had his name on way too many things. Kind of crazy, right? But again, I'm not saying Euler didn't get enough credit, because his name is still on a lot of stuff. It's just kind of crazy to think that, like, oh my god, you're just so redundant. Your name is everywhere in the math world. Let's just name it someone else who kind of assisted you or was in the background for once. Give them some credit. Give them some of the cake. You know? So, yeah, kind of interesting to think about that. But yeah, uh, E, Euler naming it E, it just shows how It's just a tribute to his genius, right? Euler, just a tribute to his genius. But now going back to this Euler's identity here. This comes from Euler's formula: e to the I theta equals to cosine of theta plus I sine of theta, which can be proven two ways from the top of from based off of what I know right now. Of course, there are probably many more. The first way is kind of the most common way, using Maclaurin's series. We wrote e to the x, cosine of x, and sine of x, and doing some manipulation to actually get e to the ix equals to cosine of x plus I sine of x. And then, of course, if you plug in pi, we get this e to the I pi plus 1 equals 0. The other way is using, I think, de Moivre's theorem and then doing some limit stuff and algebraic manipulation to get Euler's formula. And then, of course, we get Euler's identity, which is really beautiful because it combines these three fundamental symbols and elements of mathematics, e and pi, and I, and then plus 1 equals 0. It's just so beautifully composed. It's just all together in one succinct sort of equation. I've seen people getting this tattooed on their chest. It's like they're that crazy for this because of just how beautiful it is. So I find that quite fascinating and really beautiful. Like and this is actually true. In fact, if you own like a TI 84, which is like the most popular calculator in the U.S. for high school students, you could literally type in e to the I pi and you will literally get -1, which is really cool. It's like that's how aware we are of it in the math community, right? It's so beautiful. In fact, one of my favorite professors that I follow of Carnegie Mellon University, a former coach of the USA IMO team, Professor Po-Shen Loh, he made a very famous video just going over e to the I pi plus 1 equals 0 and how it's the most beautiful equation in mathematics. I'm pretty sure that was the title of the video. Really, really cool video. I recommend you watch it, guys. So I'm just gonna give some final thoughts here, just like a recap, and then you guys can ask some questions because I know you guys have a lot of questions, right? You can leave them in the chat if you want, the Zoom chat. So really, recap: E is more than just a number. It's like a gateway to understanding the universe's patterns of growth and decay. It's mysterious yet natural, flows with us. It's discovery through the study of right continuous interest, compound interest as well, to its role in defining like natural processes, like natural flows, natural patterns in our universe. E has proven itself as indispensable, right? While pi celebrated for its geometric beauty, E deserves equal recognition, all right? It's just so cool. It flows with us. It's just the natural base, natural number, right? The natural number. Okay. Um, it's not actually a natural number, though, but you guys get what I mean. It's far reaching applicability, right? So next time you encounter things with E, just remember the silent power of E. All right, remember it. So yeah, guys, I really want to thank you guys for joining me here on this lesson of E. I know it's not what you anticipated for Pi Day. You probably thought, oh, I'm going to talk about pi and pi stuff. Um, but really, I hope you've gained a new appreciation for this remarkable constant. Again, you can call it a constant, but you can't call it Euler's constant. You can call it a constant because it is a constant, but it's not Euler's constant. It's Euler's number. When you affiliate it with Euler, call it Euler's constant. If you just generalize and say, oh, E is a constant, that's allowed because that's a true statement mathematically. But in terms of the naming, it's not correct because if you say Euler's constant, that relates to the gamma, which we talked about. So yeah, guys, I plan to do more lessons. Again, just hang in there. If you don't have questions, you're welcome to leave. the call. But we're gonna go get more into logarithmic spirals, maybe some differential equations. Um, of course, also more connections with E and complex numbers. Like Euler's equation. We're gonna do some proofs on that with I'm gonna do the De Moivre's theorem and the Maclaurin series proofs later on. So really, the journey doesn't end here with E. You're gonna see it a lot. Okay, E is always gonna show up one way or another. Okay, and happy Pi Day 2024. Yeah. Okay. Questions. Mark, I'll take yours.